Welcome. In this birthday presentation, I chose something from statistics. It's a result I got about 10 years ago. If you look at random outcomes, you usually assume you have a nice distribution for the random variables. Rarely this high-risk situation. This is the delusional world. This is the real world. What happens when you look at, say, the danger of nuclear war, it's a very, very low risk, but it's not a zero risk, and it can happen, has devastating results. If you look at weather events, they are usually it's nice and beautiful like today, but sometimes there are storms and devastating results. Earthquakes, meteorite impacts can be just completely devastating, can even destroy life. And if you look at the stock market itself is a very usually quite a regular thing, but then there are these cases where you have vast drops or also vast gains in a short time. I call this the high-risk world, and I want to make this mathematically precise. It deals with random variables which have infinite variance. But still they have some still some niceness in the sense that the variance exists in an averaged way. So also the expectation usually doesn't exist for such random variable in a calculus way, but in the Cauchy principal value like defined here exists. And the prototype example is the Gaussian distribution. This Cauchy distribution is my favorite distribution. It's also my favorite because it's completely, marginalized and even considered evil. So you can look it up. It's called the Hannibal Lecter of all the distributions. It's kind of the pathological case. The function itself, which you look at, this function is called the witch of Agnesi. Also, a bad name given to this because it has this, strange behavior, pathological. If you look at statistics books, you see this especially books which actually should care about applications, like in economics. This is actually the real world. The real world is very risky, and you can look at that. You can produce such random variables very easily. You just produce the cotangent function of a random of pi times a random number between 0 and 1. So you can try that out. You push. You do that with a calculator or with a mathematic. I can maybe show a few random numbers. They are usually very nice, but then there are cases which are just brutal, where you are losing. So high risk doesn't necessarily mean that you are just risk everything, you put everything onto one number. That's still kind of a nice world which you can model with nice probabilities distributions. But what it is, for example, if you would have the green thing, you would be killed. That's kind of Russian roulette type thing where you have really severe consequences. And this is also our life. We have this thing, we are bombarded by random processes, and sometimes you get cancer, sometimes you get ill. So this world is maybe the real world. And mathematically, I just want to say something. It's a nice theorem I discovered about 10 years ago when working on these random variables. I didn't work on IID random variables. I worked on random variables which have correlations, almost periodic correlations. And in that case, it's very, very interesting what you can get there. The law of large numbers doesn't apply anymore, but you can have universality if you do the right thing. It's one of the, I think, most beautiful results I have obtained in my career, this cotangent function. If you look at maybe I just displayed the preprint, but it's a very interesting case. You look at the sum of random variables, and that produces you a stochastic process, and a sequence of random variables is a stochastic process, and then you usually in probability theory you assume that they are independent, and then any probability course with some value proves these three theorems. The first is the law of large numbers, which tells you that the average goes to the mean. Also, always in the nice case, you have some moments which exist. You have the law of iterated logarithm, which makes this more precise, and you have the central limit theorem, which tells that if you normalize the distribution so that it has mean 0 and a variance 1, then it converges weakly to the normal distribution, which is the Gaussian distribution. So any introduction first year probability course proves this, and this is usually done with some Fourier theory. So you're using characteristic functions, which is just a Fourier transform of the probability density function. So this is my definition of high risk. So first of all, the mean has to exist in a Cauchy principle. Also Cauchy, I'm a big fan of Cauchy principle value. So in the sense that it's just like the Cauchy distribution, here the mean doesn't exist, it's not L1, these are not L1 random variables, but you have to kind of take the average mean. Also here you even have to divide by. So the variance when you restrict yourself from -n to n grows like n. That's what happens here. So the standard deviation is infinite. So it's not fat tail, it's even worse. It's that you have really kind of and that's that number I call the risk, because it is also in the case of Cauchy distributed random variables. If you take Cauchy distributed random variables with a parameter c, that c is exactly the risk. So that's the relation. If c is large, so you quantify even this infinite variance by looking at these averages. So this is the risk, and so that's what we look at. We look at the class of random variables, and it's very nice. If you take the sum of two random variables in that class, they are again in that class. This is the central limit theorem is a fixed point. When you take random variables, you take two of them, you add them, and independent, and you add them, and you look at the distribution. This is a process which increases the entropy. So entropy is a very important principle. The differential entropy increases, and in the maximal case, you have this Gaussian distribution. So it's kind of like a thermodynamic point of view. So this is inevitable, this limit. But you can prove this quite simple using Fourier theory. We'll actually do that. And then there is an analog here. It's almost the same, but a little bit more, tiny bit more subtle. In that case, you also use the Fourier theory to see that it goes to the. Well, yeah, that's the high risk central limit theorem. I've not seen that before, so I mentioned it in 2012. Maybe I will write it down at one point. But what happens if you take IID high risk random variables, then the normalized sum, normalized now so that we normalize it so that the Cauchy mean is 0 and the risk is 1. So if you take that and you, some people do that by this map, you just take the average, and you end up with a Cauchy distribution. So it's also increasing entropy, and what happens is here the entropy is even larger than here. It's higher entropy distribution, this one, than this one. So how does one prove that? Just very quickly, I mean, this is the proof of the central limit theorem. There you need that some moments are finite. Usually assume that the first three moments exist so that you can make a Taylor, you can use a Taylor theorem. But what you do is you look at this Fourier transform of the PDF. Right? This is a function or measure. It's actually a measure in general. If you have not a continuous distribution, it can be a point measure. So this is a measure. This is in a generalized distribution sense meant, and this is how Kolmogorov defined the cumulative distribution function. So it's just a derivative of this cumulative distribution function. It's the density. Then you take the Fourier transform. And if you take the Fourier transform, this is phi x t. So that's well defined for a measure. So that's a function. And what happens is in the case of, you look at this map, this renormalization map, this actually means in the Fourier picture, if you take two independent random variables and you add them up, then the Fourier transforms of the distribution functions multiply, and you have this functional equation. And then you take the logarithm just to get that to get it in that form here. So which is now a linear functional equation. This you can solve. So in the case of the central limit, you have this, and if you look at that, so this means it's homogeneous. It's homogeneous of degree 2, so it has to be quadratic, and then it has to be negative in order that it is a distribution function, and then the normalization forces you to have the variance is 1, forces you to have here a 2, and that is of course coming because it's a probability density function. And then you get that, so you actually got to this Fourier transform which has this distribution as a inverse Fourier transform. So that's the proof of the central limit theorem. And in the case of high risk, this is a little bit more subtle. What you get is that you have actually kind of you have homogeneous of degree 1, but now the derivative doesn't necessarily have to exist. So if you look at this function here, this function here, this is a function where the derivative doesn't exist at 0, and that's actually possible because classically you can express the expectation as the derivative of at 0 divided by I, and the variance or the second moment is the second minus the second derivative at 0. So this doesn't here exist, right? Because the variance doesn't exist. And so this is a function which is not smooth at the origin. But again, we have a negative sign. Because that it has to be a distribution. We also have to have that the left and right slope have to be the same, and the reason is that in order that the Cauchy principal value exists, and then the normalization forces you then to have c is equal to, if you want the risk to be 1, what you have to have is that the c is equal to 1. So you have automatically, you have to have this Fourier transform, this characteristic function of the distribution you are looking for in that fixed point has to have this form, e to the minus x absolute value, and then you take the back Fourier transform, you get the Gaussian distribution here. Gaussian is also called Lorentz. So it also appears in physics in various places. So that's to the proof of this central limit theorem in the case of high risk. Okay, so I'm wrapping it up. We are going to Boston and see a concert, and this is it for today. you.